Morning. And yeah, so just I want to recall what we did last time briefly. We were mainly working with graphs which admit Eulerian cycles and Eulerian trails. Okay, so we say that given a graph, maybe a multigraph, undirected, it admits, it's called an Eulerian if there is a circuit there, which means a closed path, not using any edge more than once, such that it contains all possible edges. And the graph says to contain an Eulerian trail if we can find such a path which uses all edges and each edges once, but it doesn't have to be closed. And luckily, this is one of the big successes of graph theory. There is a very simple, nice characterization of such graphs. So namely, we were able to prove the following result, that if we have an Eulerian graph, then this is equivalent to the condition that the degree of each vertex is just an even number. And the degree of a vertex is the number of edges coming from this vertex. So it's a very easy thing to check. And yeah, the idea of the proof was that first of all, so we need to have a connected graph, of course, to start with. Then if we have a connected graph where each vertex has an even number of edges, then we can first of all find a cycle there. It doesn't have to be a Eulerian cycle. We can find a cycle of some length, non-trivial cycle, and then we can enlarge this by induction, by removing the edges of the cycle and looking at what happens in the remaining graph. Because if we're removing edges of this cycle, the degrees will be dropping by an even number, so they still will remain even. And if our graph splits in the connected components, we get smaller graphs with the same property, and we can use induction. If we know how to construct Eulerian cycles in smaller graphs with this property, we can glue those smaller cycles to one cycle we start with. This also allows us to find an algorithm how to construct Eulerian circuits. So Eulerian graphs are kind of easy to characterize and also to construct explicitly Eulerian circuits. Okay, and if we are interested in graphs admitting Eulerian trails, that means paths which uses all edges but doesn't have to be connected, then there is still a very nice simple criterion, which is actually corollary of this first result. Namely, a graph which admits a trail is just the Eulerian graph minus one edge. So in other words, the criterion would be you have to have all degrees of all vertices even, except for exactly 2. So it's a very simple observation that the number of vertices with whose degrees are odd is an even number. So it can be 2, 4, 6, and so on. But for Eulerian graphs, for graphs admitting Eulerian trails, it has to be 2, exactly 2 and nothing else. Okay, now we'll talk about Hamiltonian graphs. Let me share my screen. Yes, I'll use these notes. But I have to admit that this topic is not something I knew very well, so I'll try to do my best. Okay, so Okay, what is a Hamiltonian graph? We'll be talking about non-directed graphs in this lecture, although in the book you can find some modification with directed graphs as well. So a Hamiltonian path or a Hamiltonian cycle, so cycle is a closed path and path doesn't have to be closed, is a cycle or respectively a path which contains all vertices. It has to visit every vertex. Every vertex n exactly once. Yes. So it looks similar to the problem about Eulerian cycles, where you have to use all edges once. Here you have to visit every vertex once. But Hamiltonian finding criteria when a graph is called, such a graph is called Hamiltonian. Hamilton was an Irish nobleman who lived in middle of 19th century, I would guess. Don't quite remember by heart. So he was the one who actually created a small toy where the problem was to find, a path which visits each vertex of a certain polytope just once. So, and he was also thinking about this problem in general. Okay, so although the problem looks similarly to finding an Euler circuit, it's much, much more difficult, and there is no necessary and sufficient conditions which guarantee that a given graph is Hamiltonian, has a Hamiltonian cycle or Hamiltonian path. There is a bunch of conditions sufficient and a bunch of conditions which are necessary, but there is no criterion if and only if thing does not exist, and apparently is very, very difficult. Okay, so let me do some simple example. So small graphs are of course Hamiltonian. And now if we have a cycle, for example, of any length, cycle just, vertices on a circle and edges connecting two consecutive vertices. This is obviously a Hamiltonian graph. We go around, we'll visit each vertex once. So in particular, usual square is a nice Hamiltonian graph. Another interesting example is the graph which is obtained by a hypercube by taking its one skeleton, so to say. Don't be afraid of those words. So to start with, if you take the usual cube and just look at the edges. So you have a picture. Yeah, maybe I can draw this. I don't know. Yes, let's see. Well, can I draw this? Let's see. No, it doesn't work. I'm sorry. I can share my screen and okay, anyway. So I hope you understand what the one skeleton of the usual cube is. And then we know how to create a Hamiltonian path in the usual square. And there is a way to extend this to a Hamiltonian path which is obtained by all edges of the cube in the following way. And this is an inductive procedure which shows that for kind of cube in any dimensions, its set of edges is a Hamiltonian graph. And so how to do this? They say we do this by induction. Well, this graph can be formally defined in the following way. We don't have to think about the cube. We can think about a graph whose vertices are labeled by sequences of zeros and ones, n tuples of zeros and ones. So you have 2 power n such vertices. And an edge, you have an edge between two such sequences if and only if so these sequences are different at exactly one place. So for example, if I have a sequence 0, 0, 0, it's connected to 1, 0, 0, 0, 1, 0, and 0, 0, 1. Yeah. Now to get a Hamiltonian path, if you know how to create a Hamiltonian path for sequences for graphs for a given n, you can create a Hamiltonian path for the next dimension n plus 1. So, and here is the idea. If this is a Hamiltonian path in the graph Qn, then to get a Hamiltonian path in the graph Qn plus 1, you do the following. You put 0 v1, 0 v2, 0 v3, 0 and so on, 0 vk. So you'll get sequences of length n plus 1 here. And once you come to the sequence 0 vk, you can switch it to 1 vk. And then you do it 1 vk k minus 1, 1 vk v1. Here you are at each step, you are changing just one element in the sequence, and then you go back to 0 v1. If you think a little bit about this recipe, you'll see that it allows you to create a Hamiltonian cycle in the next dimension if you know how to do it in the previous dimension. And obviously, you can start with the plane square where the Hamiltonian cycle is just going around. So it's a nice example of a sequence of Hamiltonian graphs. Here's also a simple example of a graph which is not Hamiltonian, does not have a Hamiltonian cycle. Why? Well, let's do this small exercise. And so assume that we have a Hamiltonian cycle. If we have a cycle, then we can go around it, so to say, and we can start with any vertex. So a Hamiltonian cycle should contain each vertex once. So we can assume that we start with this internal vertex A. Now, by symmetry, we can go left. In principle, we can go left and go right, but by symmetry, that's exactly the same thing. So let's think that we go left. Then again, by symmetry, we can go up and down, and it doesn't matter. So here we can go this way and that way. So we're not making any special choices because up to symmetry, this is the unique thing to proceed. Once we're here, we have to move here. Now from here, we have to move here. And if we're going back, we'll be missing those things. So to hit the maximal number of vertices possible, we have to go down. And from here, we can only go here. And then we are stuck. We cannot make a cycle. We cannot get back to this original vertex A because we already burned those edges. So the maximal thing we can do, we can go this, and then we cannot go back because we'll be visiting this vertex 2 times. So we'll be hitting all vertices in this way, but we cannot make it into a cycle. So this graph, it contains a Hamiltonian path. It does not contain a Hamiltonian cycle. On the other hand, if we remove this vertex and just make a straight edge, it seems to have a Hamiltonian cycle. Yes, we can just go around like this. We'll not be using this intermediate edge. So we'll go just around and we are done. So we're getting a cycle. Okay, very interesting theorem, which is proven in your book. And maybe we can go and take a look.
Can I ask you a question?
Oh, yeah.
Yeah, the previous example, it was a very simple graph. So it's easy to see that it doesn't contain a Hamiltonian cycle. But is it the only way to actually show that this is true, actually brute forcing all possible configurations?
Well, there is no necessary and sufficient condition. There might be some necessary condition which is violated, but I'm not an expert. So I know some results which are in the book which give sufficient conditions for the existence. But I mean, Hamiltonian cycles is a really big area, and I can take a look if you're interested. Maybe we can chat a little bit afterwards if you're interested in this aspect. Hamiltonian graphs, I mean, they are useful. They often appear in some practical applications, but unfortunately, there is no necessary and sufficient thing. There is no criterion to check. So in many cases, you have to do some kind of ad hoc arguments to show this. Because there are some, I mean, typically a typical result giving a sufficient condition is like this. We'll see it soon. If your graph has a lot of edges, then it contains a Hamiltonian cycle. On the other hand, there are very simple graphs, like just one simple cycle where the number of edges is very, very small compared to the number of vertices. It's hardly connected, and it is Hamiltonian. But it's impossible, seems to be impossible to give necessary and sufficient conditions. Okay, so I hope it helps. And if you want to discuss things, we can probably email and discuss something after. So your book contains two interesting results. The first one I'll probably do not want to prove at the moment. I can, maybe if we'll have time, maybe I can do this a little bit later. And it says, as I said, typical result, typical sufficient conditions say that a graph which has a lot of edges has a Hamiltonian cycle. Okay, so here is a theorem. If you have a simple graph, simple meaning that it has no loops and no multiple edges, and also it satisfies the property that whatever two vertices you take and you add their degrees, the sum of the degrees should be the number of, at least the number of vertices minus one. I don't know why this is here. So yeah, so the sum of degrees of any two distinct vertices should be at least the number of vertices minus one. Then the claim is that the graph has a Hamiltonian cycle. And here there is an example that so apparently every graph, every connected graph on 5 vertices having no terminal vertex. A terminal vertex is just a vertex connected by a single edge. It's just hanging there. So if you're looking at a graph which does not have hanging vertices and has at most five of them, then it has to be a Hamiltonian. But yeah, we can also check this by hand. But as soon as you have more than, so it's obviously forbidden to have a hanging vertices. Hanging vertex automatically makes it impossible to have a Hamiltonian cycle. So it's natural to consider the class of graph without hanging vertices, and then among them, if you have very small number of vertices, there is a Hamiltonian cycle, but starting with 6, it's no longer true. Okay, and here is a little bit different result, which we can hopefully go through the proof, and it requires a little bit more than the previous one, I guess. I think this one, okay, it's similar in spirit. It says that if we have a loop-free graph and the number of vertices is at least 3. Now we are asking the following. We're looking at any two vertices which are not adjacent, so there is no edge between them. And then we want that the sum of the degrees now would be at least the number of vertices. So it's a little bit stronger in terms of the sum of the degrees. On the other hand, we only want this for vertices which are not adjacent. In the previous result, we were asking for all pairs of vertices to have this number -1, at least this number -1 edges. Okay, and the claim is that under these assumptions, G will contain a Hamiltonian cycle. Okay, so let's try to follow the argument here. And the argument is like this. I will show that, let's see if I understand this. We'll show that any subgraph which has, so, okay, yeah, one obvious remark. If we're talking about complete graphs on n vertices, they're obviously Hamiltonian, yes. So if you have a complete graph, you can very easily find there are lots of such paths which just visit each vertex 1. So you can just choose a cycle. Okay, now, so we're talking about graphs with n vertices now. And we'll be saying, consider the maximal subgraph of the complete graph which does not have a Hamiltonian cycle. And maximal in terms of the number of edges. I'll explain just in a second. Now we'll be showing that such a graph, G, has to violate this property, that the sum of the degrees, it cannot satisfy this property. And from this, it will follow that if we have a graph with a Hamiltonian property, okay, from this, it will follow that if this property is satisfied for all pairs of non-adjacent vertices, then our graph has to be Hamiltonian. So we'll be arguing by contradiction. Okay, so the number of vertices is n. G has to be connected, obviously, graph. Now we're assuming that G is maximal in terms that we cannot add any more edge to it, such that it has no Hamiltonian cycle, which means whatever edge will be adding to G will be getting a graph with Hamiltonian property, with a Hamiltonian cycle. So we want to show that for such a G, if two its vertices are not adjacent, then degree of V plus degree of W should be smaller than that. And this, by contradiction, would lead to, as soon as this thing is satisfied for all pairs of non-adjacent vertices, then G has to be a Hamiltonian graph. Okay, yeah. So what do we do? Okay, if G is maximal, look, that means that whichever two vertices, V and W, we're taking in G, which are not adjacent to each other already, And if we add this additional edge connecting V to W, then we have to get a Hamiltonian cycle, because G was maximal in this property.
What did you say maximal was? Maximal graph is
Maximal
that
was, okay, maximal graph was such a graph that if you add any edge to it, it will become a Hamiltonian. Should I repeat? Okay, so we'll be looking at
could you draw an example, maybe, of a maximal graph?
Well, okay, so but then I have to switch to iPad. Yes, okay, let's try to do this. So let me switch to an iPad. Yeah. Okay, do you see it now? Oosh, why is it not working? Gosh, something is always. Okay, now good. Okay. Do you see my iPad, by the way? Hello?
Yes, we see.
Okay, very good. Okay, so let's see. So what is it we were doing? So say let's work with 4 vertices only. That's not such an interesting example. So we're in K4, and we're looking at maximal non-Hamiltonian subgraphs. So what could it be? So I think it's like this. Oh, no. I'm sorry. So this is a maximal non-Hamiltonian subgraph in K3, in K4. Do you see this? What does it mean? It means that whatever missing edge will add to it will get a Hamiltonian graph. So this is a maximal non-Hamiltonian. Why? So we have 2 edges missing. So if we add this guy, this would become Hamiltonian. Yes, so we'll have such a path.
We're talking about a cycle now, not a path, right?
Yeah, cycle, yes. And
so is maximal only for cycle or also for path?
Well, the theorem we're discussing is now about cycles.
Okay, thank you.
I mean, in our book, there is no much discussion about the cycles, about paths. They are only saying that if you have a Hamiltonian cycle, okay, so graphs admitting Hamiltonian paths are obtained from graphs admitting cycles by removing of any edge. If you have a Hamiltonian cycle and you're removing just one edge from this cycle, what you'll get would be a Hamiltonian path. So the most of the effort is about graphs admitting Hamiltonian cycles. Okay, and if we'll be adding another edge, so we'll be getting a thing like this. Yes. And do we have a cycle here? Hopefully, yes. Let's see. Can we get the Hamiltonian cycle here? One, yes, we can. So if we start from here, go here, 1, 2, 3, and 4. Yes. So this is a maximal non-Hamiltonian graph. Is it somewhat clear now what I mean?
Yes.
Okay, so it's a maximal in the sense whatever missing edge you add on the same set of vertices, you'll get a Hamiltonian. And such graphs exist because the complete graph is obviously Hamiltonian. Okay, so let me go back to my slides. Okay. So once again, I want to prove that maximal non-Hamiltonian graph has to satisfy the property that for any non-adjacent vertices, the degree of V plus degree of W should be smaller than that. Okay. So we pick VW, a pair of non-adjacent vertices, and we know that if we add this edge, then we'll get the Hamiltonian G plus E plus this edge will become a Hamiltonian cycle. So let's write this. So V1, V2, blah, 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 Vn, where Vn is equals to V1. The last one is the first one. So let's assume that this first edge is our E. So V1 is V and V2 is W. Okay, now we're saying here that for each I from 3 to n, either the edge connecting V2, which is W, to Vi. So we're looking at all vertices in this cycle except for the first two. And for each of vertex here, we're saying that either this edge is not there, or that edge is not there. So totally we'll get that the sum of the number of edges would be smaller than that. Okay, why is this? So, okay, assume that both of them, both W, so there is an edge from V1 to this guy and from V2 to this guy. Now they are saying that, let's see. Now they are saying that we can remove this edge, V1, V2, and instead, okay, so we'll have, okay, that means that we'll get a Hamiltonian cycle already existing in G. If we use these edges going from V1 to this additional vertex here, and from V2 going to additional vertex here. And here it's constructed. So here it's explicified. So if they existed vertices from V1 and V2 to some later vertex, so then it means that already a Hamiltonian cycle existed in G. Okay, and by this requirement that for any two V non-adjacent to W, we have that either this holds or that holds. Then if we look at the total degree of the vertex V and the total degree of vertex W, they have pairwise excluding edges. So there is no edge from V and W going to one and the same vertex. That's why the sum of the degrees is at most n minus 1, where n is the number of vertices, the total number of vertices. Okay, so it's a little bit tricky argument, but not really that complicated. Okay, and there is a corollary of this thing saying that if we have again the same assumption, simple loop-free graph, and if its total number of edges is quite big, it's the number of edges on n minus 1 vertices, and the complete graph of n minus 1 vertices, n plus 2. So we're just missing very few edges. We are missing approximately n minus 2 edges to get the complete graph. Then such a graph should contain a Hamiltonian cycle. So the maximal number of edges in a graph on n vertices is n choose 2, of course, yes. Here we're taking n minus 1 choose 2 and plus 2. So the difference between n choose 2 and this thing is something like n or n minus 1. So I'm just missing very few edges. And all the results I know about Hamiltonian cycles is about graphs with very, very many edges. Okay. So here is some kind of small argument. Let me follow, not very complicated. Okay, so assume that the number of vertices is n. Take two non-adjacent vertices. So what will show that under this assumption, if we have that many edges, then we'll be satisfying the condition of the previous theorem, namely that for any two non-adjacent vertices, we'll get the sum of the degrees bigger or equal than the number of vertices in the graph. So that's why this statement is a corollary of the previous one. Okay, so we're assuming that the number of vertices is n. We're taking any two non-adjacent vertices and removing them from the graph with all their edges, of course. So we'll be getting a graph with n minus 2 vertices now. And now the number of edges would be the number of edges in the original graph minus the degree of v and minus the degree of w. This is because v and u do not have a common edge. So we're getting this new graph G with v and w removed, and so its number of edges is its number of vertices is n minus 2, and it has at most that many edges, of course, because this is the number of edges for the complete graph on n minus 2 vertices. Okay, so what does it tell us? It tells us now that, let's see, so we'll be moving these two guys to the right. So we'll have that the number of edges in G is small or equal than this guy. And on the other hand, it of course is big or equal than what? Why do I have that thing? N minus 1, choose 2 plus 2. Yeah, this I don't quite understand why. Maybe we will not need this, I hope. No, well, we probably do need that. Why is it that we? Yeah, this is, oh, sorry, this is our assumption. This is our assumption. Sorry, this is our assumption of the theorem, of course. Yes. So the number of edges, this is our requirement. The number of edges is big or equal than this thing. On the other hand, it's obviously small or equal than this thing. Okay, now we get that the degree of v plus the degree of w, now by moving this term to the other side, we get this is n minus 1 choose 2 plus 2 minus, and this is n minus 2 choose 2. And we expand the binomial coefficient. This is n minus 1, n minus 2, 1/2 plus 2, and this is n minus 2, n minus 3, 1/2. And we subtract them, we'll get n. So we're getting that for any two non-adjacent edges, the degree of v plus degree of w is at least n. Okay, that's probably everything I want to tell you about Hamiltonian graphs. And there is a famous conjecture still open by Lovash. So there are actually quite a few. So I don't think that people are still actively working on the theory of Hamiltonian graphs, because seems to be very difficult, but there are still some nice open questions left. So, for example, this conjecture of Lovász. Lovász is a very famous computer scientist and mathematician. So he studied a special kind of graphs where you have a very big symmetry group of the graph. So there is, for any two vertices, there is a graph isomorphism with itself. You can find a transformation sending vertices to vertices such that any vertex can be sent to any other vertex by graph isomorphism, by internal graph isomorphism. Such graphs are called vertex transitive. And he conjectured that and such graphs appear often in connection with finite groups. Maybe you heard about those. So finite groups have so-called, I forgot what's the name, Coxeter graphs, I think they're called. And you get graph with this property, where the vertices would be just elements of the group and the edges would be some natural coming from very, very natural relations of a group. Okay, so and then this is a very special class of groups of graphs, and all graphs which are known of this type, and there have been very huge computer searches. I think this conjecture is shown to be true on a computer up to the number of vertices equal to about 100, which is enormous if you think how many different graphs there are with about 100 vertices. But in general, it's still open. Okay, so yeah, so let's make a small break now. Okay, so 5-10 minutes. Zoom recording before I forget. So now we'll discuss another quite famous problem in graph theory. This is about colorings and chromatic polynomial of a graph. So let me share my other screen for a second. I'll try to explain where this problem started with. Okay, come on, yes, good. So coloring problems. So it was originally initiated in the second half of the 19th century, and the problem was how to color a map. So you have a map with different countries, and what you want, forgive me for my very bad drawing, so assume that you have a geographical atlas with different countries there, and what you want is, so you want to color all countries in a few colors, in only a few colors, in only a few colors, so that neighboring countries have different colors. And I think it was some Scotch or maybe English gentleman. So obviously you need at least 3 colors, because so there are countries, whatever map of the world you take, there are points where 3 countries come together. There is a common point of the boundary where at least 3 countries come in. And then you need at least 3 different colors to color them. Yes, so you need, I don't know, red, blue, and green. This is unavoidable. You can never do on a realistic map, you can never do with less than 3 colors. But 3 colors is also not enough usually. And there was this big conjecture, which is called 4-color conjecture. That any plane map where no 4 countries meet, so to say, meet at a common point, can be colored with only 4 colors. So what we do not want to allow, we do not want, typically there are 3 countries meeting. We cannot avoid 3 countries having a common point on the boundary, but we want to avoid the situation with very many countries have one and the same common point of their boundary. We do not allow that. And in the real map of the world, this never happens. So there are maximally 3 countries having a point, the common boundary, but not more. Okay, so this problem can be easily reformulated in terms of graph theory. So equivalent reformulation would be reformulation, and that's what mathematicians were working on for quite a long time. Any planar graph can be any planar graph can be colored in 4 colors. And what do I mean by that? So now I have to introduce the notion of a coloring definition, and then I'll probably go back to my slides. Definition: a coloring of a graph is a map from its edges to, say, numbers 0 to, and coloring in n colors, is a map from its vertices to the numbers 1 to n, such that no adjacent vertices are mapped to the same number. Okay, so we'll be coloring vertices of a given graph, assigning them different colors. So we have our collection of colors, which we for simplicity enumerate number 1, number 2, number 3, number n. And the requirement is that no 2 vertices which are connected by an edge should be colored the same way, should have the same color. And how it's related to coloring of the maps? Well, it's not difficult. So if you have a map, you can associate with a planar graph to a map. One can associate its graph, namely vertices are countries. So we are putting one vertex at each country, and edges are neighboring countries. So if two countries have a common piece of a boundary, not just one point, but a segment of a boundary in common, then we connect them by an edge. In this way, one problem is translated into the other. So coloring maps is the same problem as coloring this planar graph, and this graph you obtain from a plane map would be obviously planar graph, because you can draw your edge through this common point of the boundary where no other country is joining. Okay, so this conjecture about possibility to color every plane map in just 4 colors have been posed in, I don't remember, around 1870 maybe. It was supposed to be proved positively some 10 years after that. But then after 10 more years, it turns out that the proof was wrong. And it took to around 1970 when the first proof of this thing appeared, the actual proof. It was computer aided. So the authors of this proof didn't have a complete theoretical proof of this fact, that it still does not exist. There is a number of different proofs of 4-color conjecture or 4-color problem now, but all of them are at least in part computer aided. So you have to check on the computer to be able to color on the computer a rather big collection of graphs. In this original proof, there was some 2,000 graphs which they had to do on a computer. And after that, so they have reduced the general problem for all planar graphs to a huge number, but still finitely many types, finitely many planar graphs, about 2,000 of them. And this they were not doing by hands because it would be very difficult. This has been, computer were able to find colorings with 4 colors of all these things. Now this proof has been substantially simplified, but the computer element has not been completely eliminated as far as I know. Okay, now let me go back to my slides. Okay, good. Let's see. Now we'll be talking about colorings and chromatic polynomials more generally. Not just this 4-color thing, which was the start of this interesting area of research, but the general thing. So assume that we have a graph. I hope you see my screen now. We have a graph G. So n coloring of G is a map from its vertices to numbers 1 to n, such that if V and W, for any V and W which are adjacent, they are assigned different colors. So the minimal number n for which an n coloring exists is called the chromatic number of a given graph. So let's think a little bit. Maybe you can tell me, if we have a complete graph on n vertices, what's its minimal chromatic? What is its chromatic number? It's denoted by chi of G. That's a classical notation. Well, obviously, if it's a complete graph, any vertex is connected to any other. So you have to color all vertices differently. So its chromatic number is n, has to be n. Fewer than n will not work because each vertex is connected to each other vertex. Okay, so you can reformulate this in terms of the so-called graph homomorphism. I don't remember if we had the notion of graph homomorphism. A graph homomorphism between two graphs is a map from the vertices of one graph to the vertices of another, so that the edge in the first graph, so say we're mapping the graph G to the graph H. Graph homomorphism is a map from vertices here to vertices here. It doesn't have to be one-to-one. Just any map, you have to associate a vertex here, some vertex there, so that if you have an edge here, then there will be an edge between the images, between the imaging vertices. Okay, so in this way, using graph homomorphism, we can say that graph coloring, so which is a map from the vertices to, say, elements of 1 to n. So we get the graph coloring by mapping vertices of this guy to numbers 1 to n, if and only if it would be a graph homomorphism between G and the complete graph with vertices from 1 to n. So it would be a graph homomorphism from G to Kn. Okay, and the proof is here. It's very, very simple. So by definition, a map from the vertices of G to numbers 1 to n is an end coloring if for any V incident adjacent to W, we have that the images are distinct. And this is, yeah, this is if and only if every edge of G is mapped to an edge of the complete graph. So that's in a sense a tautology. So let's now, as I said, obviously Kn has its chromatic number n. So how many colorings are there if we allow to so if we want, let's see. So if we now use M colors instead of N instead of N, how many colorings are there in M different colorings? And the claim is that we have to choose. So we have to look at N colorings of Kn. And multiply it by this m factorial divided by n factorial, which is the number of ways to choose n colors among m. Yeah. So what we have to do for a complete graph, if we have more colors than n, so we have to choose a sub-collection of n of them because we only have n vertices to color, and then multiply by the number of possible colorings of Kn. In any case, an obvious trivial corollary of this observation is that the chromatic number is obviously at most the number of vertices in a graph, because we can always color a graph coloring each vertex in its own color. Yeah. So the chromatic number is something in between 2 and the number of vertices. If you have at least one edge in your graph, then you have to use 2 different colors for vertices, adjacent vertices, and then you have the upper bound on the chromatic number, which is the total number of vertices. Okay, so here are some simple examples. So for a cycle, its chromatic number is 2 if the number of vertices is even. For example, for a foreground, we can color it black, white, black, white. And if we have 5 vertices, it will not work, because if we have 5 vertices, we'll start black, white, black, white, black. And then we have this thing. We cannot, yeah, this will not work. So we have to use 3 different colors if we have a cycle with an odd number of vertices, and 2 colors for a cycle with an even number of vertices. Now, there is a simple proposition characterizing graphs whose chromatic number is 2. I said every non-empty graph needs at least 2 colors. And what are graphs which can be colored with exactly 2 colors? Well, these graphs are called bipartite. I recall what a bipartite graph is. Bipartite graph is a graph where you can split all vertices into 2 disjoint groups, V1 and V2, so that all edges go in between V1 and V2 only. There are no edges inside the first group and inside the second group. And if you have such a situation, well, then it's trivial. You can definitely color it in 2 colors. You color one group white and the other black. And vertices and edges all go in between white and black only. And this is also works both ways. So this shows that the bipart graph is 2 colorable. Also, if you have a graph which you can color with black and white only, then you say that I declare that my white vertices form one part of my graph and my black form the other one, and the edges would be just in between them. And in this way, you see immediately that the graph is a bipartite graph. Okay. So let's look at the Pedersen graph, which we had before. So it's a graph like this. It's 2 regular 5-gons, one like this and one like this, the other one inside, and with pair of edges connecting, these corresponding vertices here. And here we have a cycle like this, and here we have this star edges forming this Soviet star inside. And the claim is that the chromatic number of this graph is 3. Why is that? Well, first of all, we can produce such a coloring. Well, we can see that it cannot be 2. Why? Well, because it's not a bipartite graph. In a bipartite graph, all cycles has to be of even length. And here we see a cycle of length 5, so it cannot be a bipartite graph. And we can obtain its 3 coloring as it's shown on this picture. Yes, so this is an explicit 3 coloring of Pedersen graph. Okay, so what do I want to tell you more? So the important thing is, so we'll denote by the nth chromatic number for a given number of colors n. We first of all, we assume that our vertices, our graph G, its vertices are labeled. So we're not considering G up to isomorphism, where we know this is vertex number 1, vertex number 2, and so on. All vertices are labeled. And we're looking at all possible different colorings of this graph, which is again mappings to Kn if you want, or to sequence of numbers from 1 to n, such that neighboring vertices will be mapped to different elements in 1 to n. So this is called the number of n colorings. It can be 0. If n is small, if there is no coloring, say if we don't have a bipartite graph, so chi G of 2 would be 0. But we know that if if n is the number of vertices or bigger, then this would be non-zero, because each graph admits at least a coloring in the number of colors equal to its number of vertices. Okay. Mm-hmm. Yes, so let's see. I will be now introducing a polynomial p, which will depend, it would be probably better to write g as an index. It would be a polynomial with variable n, and depending on the graph, such that it's if we calculate its value for a given n, for example, n equals 2, n equals 100, we'll get the number of colorings of g in that number of colors. So pg of 100 would be how many ways there are to calculate, to color given graph g into 100 different colors. Okay, so and the way to do this would be, we have to introduce, so we'll be showing that we'll be introducing this graph by induction on the number of edges and the vertices. And the most important thing will be proving that there are two operations on the graph, and there is a very simple relation between this chromatic polynomial. This is called the chromatic polynomial of a given graph for the original graph and for graphs obtained by these two operations. And they are called deletion and contraction. And so the operation deletion is just removing an edge from a graph. And the operation contraction is contracting an edge, identifying the vertices which are associated to this edge. Let me probably switch to the material from our book, because it's a little bit better. So I hope you still see my screen now. If not, please shout. Okay, so let's see, deletion and contraction. I think I saw some nice picture here. Okay, so this picture, this figure 1190 explains what a deletion and contraction is. So we have a given graph G, and we will be, so the vertices are labeled A, B, C, D, and we have a chosen edge E here. So we have two operations. One operation is just to remove this edge and keep all vertices. So this is this guy, G sub E. This is just to delete the edge E from the graph. And another operation is contraction. So we're looking at edge E. It has bounding vertices A and B, and we're kind of shrinking them together. We're identifying A and B. So we're identifying A and B, and we are drawing all from this new vertex. So the rest of the vertices are still there. But from this identified vertex, we draw all edges which the initial graph either had between A and the rest of the vertices, or between B and the rest of the vertices. This thing we are collapsing to a point. So here it is shown what will happen. What will happen if we collapse the edge E. And now the main result, which is also useful in terms of calculations, is the following, that the chromatic polynomial So this is the polynomial whose value at lambda will be giving us the number of different colorings of the graph G in lambda colors. So in my notes, this lambda was denoted by n. And the claim is as follows, that the chromatic polynomials with an edge deleted equals the chromatic polynomial of the original graph plus the chromatic polynomial of the edge contracted. Typically, it's written this way, that this equals that minus that. So to say that we're expressing the chromatic polynomial of our original graph as the difference between the chromatic polynomial with an edge deleted and the chromatic polynomial of the edge contracted. Anyway, let's show this formula. So we're in this situation. Say E is connecting vertices A and B. Now we're looking how many ways are there to color this graph with this edge deleted. Yes, so we're looking at this graph and counting how many different colorings are there. This number should be big, of course, because the fewer edges we have, there are less restrictions on colorings. We'll be getting more colorings if we just remove some edges from our original graph. Okay, so the colorings of this guy would be split into two groups. One where A and B are colored differently, and those where A and B are colored the same color. Yeah. Okay, if A and B are colored differently, each such guy would be actually a coloring of the original graph, because if A and B are colored differently, we can throw this edge back, and this would be a coloring of G. The coloring we had would be the coloring of the original graph as well. Okay, yeah. Now, assume now that we're looking at colorings where A and B are colored the same. Then we are saying that such a coloring is in fact a coloring of this graph, a graph with this edge contracted. Yeah. And in this way, we get this fundamental relation. It helps, for example, we can easily calculate what happens with small graphs or with graphs with very few edges. What would be their chromatic polynomial? Let's see. So here we are calculating, for example, the chromatic polynomial of the square, and we are saying that yeah, so let's see. So this should be the difference between this guy and that guy. So and now the claim is that this thing has its chromatic polynomial lambda times lambda minus 3. Why is that? Okay. So let me look at this example 1134C. What does it say? Okay, so there are some basic examples of chromatic polynomials. Okay, first of all, if G has only isolated vertices, no edges at all, then its chromatic polynomial is just lambda power n, yes? Which means that, yeah, so if we look its value at, if lambda equals k, so we're having k vertices, and for each of our, we're having k colors, and since our vertices are isolated, so they are we can choose any color of this k for any of these vertices. We get totally k power n different colorings. Yes. Okay, this is one thing. Another example is that for a complete graph with n vertices, its chromatic polynomial should be the product lambda, lambda minus 1, lambda minus 2, and so on, lambda minus n plus k. And this number is denoted by lambda with these square brackets around n. This is called the 10Hamil symbol, by the way. And why is this true? Yes, well, if we color any vertex, if we say we have m different colors, or k, I was using k different colors. If we color any vertex, then for the remaining vertices, we can just use k minus 1 colors, because we cannot use the one we used for the first one. And if we used 2 colors, we have left k minus 2 colors for the next one, and so on. So this would be an easy exercise to check. So this would be the number of possible colorings. And it's obviously it's non-zero, so we cannot use fewer than n colors. This would be 0 otherwise. Because if we use 1 color, this factor will kill it, 2 colors, this factor will kill it, and so on. N minus 1 colors, this factor will kill it. So the first non-trivial coloring we'll get with n colors, and this will be n factorial different colorings. With n vertices, we can assign any color to any vertex, but then for the remaining, for the second vertex, we have n minus 1 colorings, and so on. The value of this polynomial for lambda equals to n equals n factorial. Okay. Yeah, so now for a path, the next thing is that for a path, it seems like that we have lambda times lambda minus 1 power the number of vertices in the path minus 1. And why is that? Yeah, well, that's again quite simple. So we can, so here is our path. For this guy, we can use any of our coloring, any of our colors, lambda. Now for the next one, we can use any but this guy, so it would be lambda minus 1. For this guy, we can use any by this, again, lambda minus 1, and so on. So the total answer would be lambda times lambda minus 1 power the number of vertices n minus 1. Okay, now with these examples, we can probably go back to here and try to calculate using our fundamental formula, that chromatic polynomial with a deleted edges equals the original chromatic polynomial plus a chromatic polynomial with a contracted edge, to work out the chromatic polynomial of this graph. So this is a guy with a deleted edge E, and this is a guy with a contracted edge E. So if we contract this edge, we'll get a triangle like this. So for a triangle, we know that its chromatic polynomial is lambda times lambda minus 1 times lambda minus 2. We just derive this. And for this thing, we have a path. It's lambda times lambda minus 1, 1, 2, 3 cubed. So this guy has a chromatic polynomial lambda times lambda minus 1 cubed. And this guy, as I said, has lambda, lambda minus 1, lambda minus 2. As a total, we get that the chromatic polynomial of the square is this minus that, which gives us lambda to the fourth minus 4 lambda cubed plus 3 lambda squared minus 3 lambda. So in particular, for one color, if lambda equals 1, this should vanish, and this should always be true for all graphs with at least one edge, so they cannot be colored in one color. Now, if lambda equals 2, if the number of colors is 2, this graph is too colorable. It's a bipartite graph. And there are two ways to do this. We either color white, black, or we color black, white, black, white. So there are exactly two colorings. And if we substitute lambda equals to 2 here, we'll get 2, in fact. 16 minus what? 24 plus, what do I get here? So here I get 8 times, no, sorry. So this is 16, this is 32, this is plus 24, and then minus 6 again. So we'll be getting 2. Okay, so I think this is it I wanted to discuss with you today. There are just a few more examples of calculations of chromatic polynomials, but you'll probably do it on the exercises. And I'll be posting this soon, and I hope you understood some of it. Okay, thank you, and see you next time.